Hey everyone, and welcome. Today, we're going to crack the code on motion itself. We're diving into the incredibly powerful rules that Sir Isaac Newton laid out for us, the physics that connect everything from a rocket launch to a game of pool. Let's get right into it.
So what do they have in common? I mean, they seem about as different as you can get, right? But believe it or not, they are all governed by the exact same simple set of principles. It all comes down to Newton's laws of motion and this little thing called momentum. And by the end of this, you're going to see exactly how.
Okay, so first up, the rules of motion. Before we can get to the cool stuff, we've got to build our foundation with the basics: force, mass, and inertia. You know, inertia is something you feel every single day. Think about when you're in a car and it suddenly takes off. You feel like you're being pushed back into your seat, right? Well, that's not a push. That's your body's inertia resisting the change in motion. And the more stuff or mass something has, the more inertia it has. It's just harder to get moving and harder to stop. And that leads us perfectly into Newton's first law. You can think of it as the law of inertia. The main idea: objects are kind of lazy. They just keep on doing whatever they're already doing. If they're sitting still, they'll stay still. If they're moving, they'll keep moving at the same speed and in the same direction unless some outside force comes along and messes things up. So that outside force is what we call a resultant force. It's what you need to change motion. The first law is all about what happens when there's no resultant force. But what happens when there is one? Well, that's where Newton's second law comes in. And this is where we get to put some numbers on it. The second law is so powerful because it doesn't just say things speed up. It tells us exactly how much they speed up. It gives us this perfect little relationship between how hard you push, how much stuff you're pushing, and how much acceleration you get out of it. And yeah, it's probably the most famous equation in all of physics.
And there it is, F equals m times a. It looks simple, but it's so powerful. It tells us two things. First, if you want more acceleration, you got to apply more force. Makes sense, right? Push harder, it goes faster. But it also tells us that for that same exact push, a heavier object, one with more mass, is going to accelerate less. This single equation is the key to, well, pretty much calculating all of motion.
All right, next up we've got Newton's third law. This is all about what happens when two objects interact with each other. You probably know this one as, for every action there is an equal and opposite reaction. And what that really means is that forces never, ever exist alone. They always come in pairs. You literally can't push on a wall without that wall pushing back on you with the exact same amount of force. Now this is absolutely crucial to understand because a lot of people get this part wrong. For a pair of forces to be a true action-reaction pair, they have to follow these rules. They act on two different objects, they're the same size, they point in opposite directions, and they have to be the same kind of force, like both being gravitational forces. A rocket launch is just the perfect, most epic example of this. The rocket engine violently pushes hot gas down. That's the action. And in return, the gas pushes the rocket up with an identical but opposite force. That's the reaction. That upward push is what gets that massive machine off the ground. Okay, so we have the three laws of motion down. Now let's bring in another concept that's super useful, especially when things start colliding. Let's talk about momentum.
So to get us thinking, let me ask you a question. Which do you think has more momentum? A tiny bullet moving super fast or a huge train just chugging along slowly? It's a bit of a trick question because momentum isn't just about speed. It's really about how much oomph something has, how hard it is to stop.
And the numbers don't lie. It's not even close. Momentum is just mass times velocity. And even though that bullet is flying, the train is just so massive that its momentum is 10,000 times greater. It has way more quantity of motion. Now what's really cool is we can actually go back and rethink Newton's second law using momentum. It turns out F equals ma is kind of a special case. The more complete, fundamental definition is that force is the rate of change of momentum. This is a much bigger idea, and it even works for things that change mass, like a rocket burning off its fuel. And this idea is literally a lifesaver. It's the physics behind airbags and the crumple zones in your car. Think about it. In a crash, you have to go from moving fast to a dead stop. That change in your momentum is a fixed amount. But if an airbag can make that stop happen over a slightly longer period of time, even just a fraction of a second, it dramatically reduces the force your body feels. Same change in momentum, but spread out over more time means a much smaller and more survivable force.
Okay, time for a quick but really important detour. Let's clear up a super common point of confusion, the difference between mass and weight.
So many people use these words interchangeably, but in physics, they're totally different. Mass is just the amount of stuff an object is made of. It's measured in kilograms and it never ever changes, no matter where you are in the universe. Weight, on the other hand, is the force of gravity pulling on that mass. It's measured in newtons. So you'd weigh a lot less on the moon, but you'd still be made of the exact same amount of you.
And that's why we actually use different tools to measure them. A balance scale, like the one you see in a science lab, compares an unknown mass to known masses. It's measuring mass directly. But a spring scale, like in your bathroom or at the grocery store, is actually measuring the pull of gravity. It's measuring weight.
All right, enough with the theory. The best way to really get a feel for these laws is to get our hands dirty and see them in action. Let's walk through a couple of classic physics problems together.
Okay, here's our first one. This is about as straightforward as it gets. We've got an object, we know its mass, and we know exactly how much we want to accelerate it. The question is simple. How much force do we need?
This one is a perfect plug-and-chug problem. We just pull out our trusty formula, F equals m times a. Then we substitute the values we were given, 1.5 kilograms for the mass and 2.2 for the acceleration. Do a quick multiplication, and bam, we get our answer, a force of 3.3 newtons. Simple as that.
Okay, let's ramp up the difficulty just a little. This next one is a bit more involved. It's got a few extra steps. We need to figure out the braking force needed to stop a pretty heavy, fast-moving car in just 11 seconds.
So the trick here is we can't just jump straight to F equals ma, because we don't actually know a, the acceleration yet. We have to find that first. We know the car's speed changes from 22 meters per second down to 0, and it does that in 11 seconds. That calculation tells us its acceleration is -2. Now we can use F equals ma. We plug in the car's mass, our new acceleration, and we get the required braking force, 3,000 newtons.
All right, you've seen the laws, you've seen the concepts, you've seen the examples. Now it's your turn. Let's run through a couple of questions to see how well you've got this stuff down.
Okay, first question. This one is all about the change in momentum. Now, I'll give you a little hint. Remember that momentum has a direction. That's super important here. Feel free to pause and work it out for yourself.
And the answer is C, 1.5. How'd you do? The key was remembering that when the ball rebounds, its velocity becomes negative. So its initial momentum is positive 0.9, but its final momentum is negative 0.6. The change is the difference between those two, which gives us a total change of 1.5.
All right, one last question for you. This one is more of a concept check. We talked about that more fundamental, more complete version of Newton's second law. Which one of these formulas correctly describes it?
And the correct answer is C. Force equals the change in momentum divided by the time it took for that change to happen. It's really the most powerful way to think about what a force actually is. It's simply a measure of how quickly you can change an object's momentum.
So there you have it. From the smallest collision to the grand dance of the galaxies, it's all governed by these few, surprisingly simple rules. They're elegant, they're powerful, and they're absolutely everywhere. So the question I want to leave you with is this. Now that you've seen the physics behind it all, what's an everyday motion, kicking a ball, pushing a shopping cart, anything, that you'll never look at the same way again?